The following video is on series. We'll start with the following notation. If a sub m plus 1, a sub m plus 2, all the way out to a sub n are all real numbers, we can write the following thing. So we have the capital Greek letter sigma. Below it we have I equals m. At the top we have n. And to the right we have a sub I. And this notation will mean a sub m plus a sub m plus 1 plus a sub m plus 2 all the way out to plus a sub n. We read this notation as the sum as I goes from m to n of a sub I. Let's look at some examples. So for the first example, we're looking at the series or the sum as I goes from 1 to 5 of the function I squared. We will expand this out to be 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. So notice that I starts at 1, that's the value at the bottom, and we keep increasing I by 1 until it stops at 5, which is the top value for I. If we simplify this, we'll see that we end up with the number 55. Let's look at another example. So the sum as k goes from 2 to 4 of 1 over k. So in this example, k starts at 2, and it keeps increasing each time by 1 until we get to 4. So we get 1 over 2 plus 1 over 3 plus 1 over 4, and then we stop. To simplify this, we'll have to find a common denominator and then add the fractions to get 13 over 12. Let's look at another example. The sum as j goes from 0 to 3 of 7. Notice that the function in this case is 7. So in other words, no matter what I plug in for j, the output is always going to be 7. I'm still going to start j at 0, and I'm going to keep adding 7 each time until j becomes 3. So I end up with, when j is 0, the number 7, plus when j is 1, the number 7, plus when j is 2, the number 7, plus when j is 3, the number 7. So in other words, I get 7 plus 7 plus 7 plus 7, which ends up to be 28. We have several laws that we can apply to these series. The first is that the sum as I goes from m to n of ai plus bi is the same thing as the sum as I goes from m to n of ai plus the sum as I goes from n to n of bi. This is because the order that we add things in doesn't matter. So I could first add the a's and b's together and then add them up as I increases, or I could add all the ai's together and then all the bi's together. The second law allows me to also do the same thing but with subtraction. So I can do ai minus bi, and I can split the sum up as the sum as I goes from m to n of ai minus bi equals the sum as I goes from m to n of ai minus the sum as I goes from m to n of bi. The next law is that the sum as I goes from m to n of c times ai, where c is a constant, can be written as c times the sum as I goes from m to n of ai. So in other words, I can factor the c out of every term of the sum. Now it's time to hear the story of little Gauss. When he was very young, Carl Friedrich Gauss was in elementary school at the time, and he and his classmates were, I guess, being rowdy, and the teacher wanted to give them an assignment. The teacher wanted them to find the sum of all the whole numbers from 1 to 100. Well, Gauss was very clever. Gauss said, let's let s be the sum of all the whole numbers from 1 to 100. And he noticed that it didn't matter if he wrote it backward or forward. S was still going to be the same value. He then noticed that if he added these two strings of numbers up column by column, he would get 2s equals, and then each column ends up being 101. So for example, 100 plus 1 in the first column to the right of the equal sign, 100 plus 1 is 101. In the second column, we see 2 plus 99 is 101. And similarly, 3 plus 98 would be 101, and so on all the way down the row. That means that he's adding 101 to itself 100 times. So therefore, 2s equals 101 times 100. But Gauss realized that he didn't want to solve for 2s, he wanted to find s. So he divided both sides by 2 and ended up with the answer 50/50. Needless to say, the teacher was quite shocked with Gauss's solution. Most of the rest of the students had only started the problem, and Gauss had already come up with the answer. It turns out that later on in life, this teacher was one of the main influences of Gauss, and the teacher actually helped Gauss get his start as one of the world's most famous mathematicians. It actually turns out that Gauss's technique works in general. If we're looking at the sum as I goes from 1 to n of I, we let s be the sum, 1 plus 2 plus all the way up to n. And we know that the sum will still be the same number if we write it backwards. So n plus n minus 1 plus n minus 2 down to 1. We then add these up column by column, and we see that we'll get 2s on the left side of the equal sign, and we'll get n plus 1 on the right for every column. This means that we've written n plus 1 adding to itself n times, which is the same thing as n times n plus 1. But we, remember, don't want to find 2s, we want to find s, so we divide both sides by 2. Therefore, in general, we have that the sum as I goes from 1 to n of I is n times n plus 1 over 2. Notice that this only works if I starts at 1, and if the function a sub I is the function I. We'll also have some other shortcuts. So here at the top I've written Gauss's shortcut for the sum as I goes from 1 to n of I. Let's look at another one. The sum as I goes from 1 to n of I squared. It turns out that this goes to n times n plus 1 times 2n plus 1 over 6. So as long as I starts at 1 and ends at n, and the function is I squared, we know that the sum will always end up as this value. There's also a value for I cubed, so the sum as I goes from 1 to n of I cubed is n times n plus 1 over 2 quantity squared. This should look really familiar because this is just the formula for Gauss's series, but the value ends up being squared at the end. Unfortunately, at this stage, I'm going to ask you to memorize these three formulas. If you take some more advanced math classes, you'll probably see how to prove that the last two series actually hold. But for now, all I care about is that you know how to apply these formulas. So please memorize these. There are formulas for some of the higher powers of I, including I to the 4, but for now we're not going to worry about any of those because some of the formulas get a little bit crazy. So let's look at the following. Let's say I wanted you to find the sum as I goes from 1 to 100 of I squared minus 3i. You could start by letting I equal 1, and then I equal 2, and then I equal 3, and you'd have to keep going all the way until I equaled 100. Notice that plugging this in and adding this up would take a really long time. Instead, what we can do is use the shortcuts. So we know that the sum rule and the difference rule allow us to separate this into two sums. I have the sum as I goes from 1 to 100 of I squared minus the sum as I goes from 1 to 100 of 3i. Now I know that I'm allowed to pull the 3 outside of the sum because it's a constant multiple. So now I have the sum as I goes from 1 to 100 of I squared minus 3 times the sum as I goes from 1 to 100 of I. Now I can just apply the formulas from the previous slide. So we know that the formula for the I squared is n, which in this case is 100, times n plus 1, times 2n plus 1 over 6. So I get 100 times 101 times 201 over 6. Now I'm going to do minus 3 times, and then Gauss's formula, where n is 100, so I'll get 100 times 101 over 2. Now we just have to simplify these, and I end up with 338,350 minus 15,150, which comes out to 323,200. Let's try another problem. So here I'm going to try to find the sum as I goes from 1 to 50 of the quantity I squared plus 1 times I. Unfortunately, we don't have a product law that tells us how to deal with products of sums. So instead what I'm going to do is distribute the I through the parenthesis. So I end up with the sum as I goes from 1 to 50 of I cubed plus I. Now I can use the sum rule to break this up into two sums, and then I just have to use the cube formula and the single I formula. So remember, the cube formula looks just like Gauss's formula, but squared. So I'm going to get 50 times 51 over 2, quantity squared, plus 50 times 51 over 2. In each case, I can simplify, and I end up with 1275 quantity squared plus 1275, which ends up to be, let's see, 1,626,900. Once again, this last step is not as important. You'll certainly be using a calculator for this, but what's important is that you can do the first few steps. Let's try another example. So the sum as I goes from 5 to 100 of I. Notice that in this case we do not start I at 1, so we can't just use Gauss's formula. Notice, however, if I did start the sum as I goes from 1 to 100, that the only things that I have to subtract off are the first 4 terms, because then what's left is the sum from 5 to 100. So I can rewrite this as the sum as I goes from 1 to 100 of I minus the sum as I goes from 1 to 4 of I. These are both easy sums to solve using Gauss's formula. I end up with 50/50 minus 10, which gives me 50/40.